This video covers Chapter 13, General Rules of Probability. So we started probability in Chapter 12, and we're going to build on it in Chapter 13. So in Chapter 13, we covered the general addition rule, independence in the multiplication rule, conditional probability, the general multiplication rule, how to show events are independent, tree diagrams, and Bayes' rule. So here are the probability rules we covered in Chapter 12. So rule 1 is that any event has a probability between 0 and 1 of occurring, right? 0 means it's not going to occur. 1 means for 100% it's definitely going to occur. Rule 2 is if S is the sample space, P of S, then the probability of something in the sample happening is 1, right? S is our whole sample base. So for example, our sample space for flipping a coin is heads and tails, right? The probability of that occurring has to be 1. Rule 3 is the addition rule for disjoint events. Then the probability of A or B is the probability of A plus B. So these are events that don't overlap, like flipping a coin. But we aren't going to just work with disjoint events this chapter, so keep that in mind. And then for an event A, the probability that A does not occur is 1 minus the probability of A, right? And the probability of everything in the sample space occurring is 1. The probability of A occurring is something less than 1, so if we subtract it from 1, we get the probability of it not occurring, or its converse. Now, I just said we aren't just working with disjoint events this chapter, so let's talk about how to visualize them using a Venn diagram. So sometimes it's helpful to draw a picture to display relations among several events, right? A picture that shows our sample space S as a rectangular area and shows events as areas within S are called a Venn diagram. So two events that are disjoint could be like heads and tails, right? And then if two events are not disjoint, they're going to overlap. So let's say we're rolling a 6-sided die. And let's let A be rolling an even number and B be rolling a prime. Okay, so when you roll a dice, the prime numbers are 2, 3, and 5, right? When you roll an even number, it's 2, 4, and 6. Well, there's some overlap there, right? They actually both have a 2, so we'll put 2 in the center, right? And this would be showing that those two events have an outcome in common. So, our general addition rule is this. We know that if A and B are disjoint events, the probability of A or B is the probability of A plus the probability of B. But the addition rule for any two events that may not be disjoint is going to be the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B, because what we're doing over here in this middle section is we'd be double counting, right? So if I have the probability of rolling an even or prime, we have the probability of rolling an even plus the probability of rolling a prime minus the probability of even and prime. And means both, intersection. So even is 1/2, prime is 1/2, right? That gives me a whole, but we've got some odds, right? So I have like 2, 3, 5, 4, 6, right? The overlap is important, so I subtract 1/6, right? So that's going to give me 5/6 because I have everything up here except a 1. So let's work through another example. So print books continue to be a much more popular format than books in digital format. Cool. A 2019 survey found that 65% of adults had read a print book, we'll call that B, in the preceding 12 months, and 25% had read a book in a digital format. And 18% had read both a book in print and a book in digital format. So if I want to choose an adult at random, what's the probability that they read a book in print or a book in digital, or both, right? We just want to know if they've read a book. So we take the probability of a print book plus the probability of a digital book and minus that overlap, right? Because they're going to be included in both of these groups and they're being double counted. So I get 0.72, which means 72% of adults read a book in the preceding 12 months. Next, we're going to talk about independence and the multiplication rule. So if two events A and B do not influence each other, if knowledge about one does not change the probability we assign to the other, then the events are said to be independent of each other. And I want to know the probability of two independent events occurring. Well, two events, A and B, are independent if knowing that one occurs does not change the probability we assign to the other occurring. Note this isn't the same thing as disjoint, which I'll talk about in a minute. But if A or B are independent, then the probability of A and B is the probability of A times the probability of B. So, a few notes about this multiplication rule. It can extend to collections of more than two events, provided all the events are independent. Be careful not to confuse disjointness and independence. If A and B are disjoint, then the fact that A's occurs tells us that B cannot occur. So that's very dependent, right? If I flip a heads, I know I can't flip a tails, right? Those would be disjoint, but they're not independent. And the special multiplication rule holds if A and B are independent, but not otherwise, right? Conditional probability is the probability we assign to any event, to an event that we can change if we know some other event has occurred. Let me say that again. Okay. The probability we assign to an event can change if we know some other event has occurred, right? The probability I'm going to buy icing if I've already bought cake mix is very high, right? So this idea is key to many applications of probability. When we are trying to find the probability that one event will happen, given the information that the other event is already known to have occurred, we are trying to determine a conditional probability. So if I have an event that's probability isn't zero, the conditional probability of B given A, that's what this means, B given A, is the probability of A and B divided by the probability of A. So why don't we go ahead and work through an example. So, consider imported motor vehicle sales in the United States. There. Okay, if we consider only the medium and heavy trucks, what's the likelihood of randomly selecting a sale being a NAFTA vehicle? Okay, so we've got NAFTA, other, and the total number of car sales. So the probability of NAFTA, given it's a medium to heavy truck, is going to be the probability it's a medium NAFTA and medium heavy truck, which would be this, right? That's the probability of both, divided by the probability of being a heavy truck, which is 230,717. I don't like the way they set this up. Right, so it's out of everything, right? We have to divide it by the total number, and this would give us the probability. I don't know why I didn't go ahead and calculate that for us. So I take the probability of being NAFTA and a heavy truck. That's going to be 189,722 over our total number of cars. Then I'm going to put that over the probability of being a medium heavy truck. That's going to be 230,717 over that 8.5 million or so. That gives me 0.022 over 0.027, which gives me 0.81, so 81%. This is a good example of conditional probability. Next, we have the general multiplication rule. So the definition of conditional probability reminds us that in principle, all probabilities, including conditional probabilities, can be found from the assignment of probabilities to events that describe a random phenomenon. So we need to assign probabilities to our events. More often, however, conditional probabilities are part of the information given to us in a probability model. And the definition of conditional probability then turns into a rule for finding the probability that both of two events can occur. So the definition is this. The probability that two events A and B happen together can be found by the probability of A and B given would be the probability of A times the probability of B given A. So here, the probability of B given A is the probability that B occurs given the information that A occurs, right? And so I've got the probability of A and B is the probability of A, and this could also be written as the probability of A and B over the probability of A. So we can kind of see where this comes from. These cancel, and I'm just left with the probability of A and B. And this can be extended to any number of groups of events. It doesn't just have to be two events. So, an example. The Pew Internet and Technology Project finds that 91% of Gen Xers use the internet and that 89% of online Gen Xers say the internet is a good thing for them personally. What percent of Gen Xers are online and say the internet is good for them personally? So the probability they're online is 0.91, and the probability the internet is good for them is 0.89. And this is conditional because they're already on the internet. So the probability they think that the internet's good for them given they're already online. So online and good for them personally. So the probability online times the probability the internet is good for them personally gives us 0.91 times 0.89. So I get 0.8091, so 0.81. Say are online and good for them personally. Let's talk about how to show events are independent. So the conditional probability is generally not equal to the unconditional probability. If knowing A occurs gives us no additional information about B, then A and B are independent events, right? And if A and B are independent events that both have positive probability and are independent, that would mean the probability of B given A is the probability of B. So I actually really like tree diagrams. We learned how to describe the sample space as of a chance process in chapter 10, right? But another way to model chance behavior involving a sequence of outcomes is a tree diagram. So let's consider flipping a coin twice. What's the probability of getting two heads? So here's our sample space. I can get two heads, head, tails, tails, heads, or tails, tails. So if I toss a coin, I can either get heads or tails, and then I toss it again, and I can either get heads or tails. So we multiply these probabilities. So the probability of two heads is 1/4. The probability of heads and tails is 1/4. Probability of tails and heads is 1/4, and the probability of tails times tails, we're multiplying these again, is 1/4. And we could see that from looking at our sample space, but sometimes making a tree diagram can really help us see our sample space. So the probability of two heads is 1/4. Let's do another example, because I really do like these. So Looking only at adults under 65, about 17% are 18 to 24-year-olds, another 41% are 25 to 44-year-olds, and the remaining 42 are 45 to 64 years old. Pew Research reports that 27% of those aged 18 to 21 have used online dating sites, along with 22% of those aged 25 to 44 and 13% of those over 45. What percent of Americans under 60 have used online dating sites? So we could set this up, right? So 17% of the population is between 18 and 24. 41% is 21 to 44, and 2% is 45 to 64. Then we look at each of the breakdowns on dating. So 27% of those have used an online dating site. That means 73% haven't, right? Because it has to add up to 100. 22% of those between 25 and 44 have, and that would mean 78 have not. And 13% of those aged 45 and over have, and 87 have not. So we multiply these probabilities together to get the probability. So I want to know what percent of Americans under 65 have used an online dating site. So I want to look at all these people. So I want to find the percent of adults 18 to 24 who have used a dating site. Yes. So I'd need to multiply those two together. 0.17 times 0.27 is 0.0459, right? But I also need this one, right? I need the probability that 25, 44, and yes to online dating. So that's going to be 0.41 times 0.22. That gives us 0.09. And then I look down here, I need this one as well, the probability 45 to 64, and yes, online dating. That gives me, I have to multiply, 0.42 times 0.13, so I get 0.055. So I can go ahead and add this up. So the probability they're under 65 and online dating, as each of these groups are independent, we can add them together. That's 0.0459 plus 0.09 plus 0.055. Sorry, I'm adding. So that would give me 0.1909. So we could say 19%. So 19% of adults under 65 have used an online dating site. The last thing we're going to discuss in this chapter is Bayes' rule. So Bayes' rule provides an important unifying structure and is a basic result in an important area of statistics known as Bayesian statistics. So thinking about the last example, we were given the probability of online dating in 18 to 24-year-olds was 27%. So if we chose an random 18 to 24-year-old, the probability that he or she had used an online dating site is 0.27. But what if we want the probability of 18 to 24 given online dating? So the probability that if we chose an online dater, they'd be 18 to 24. And for that, we need Bayes' rule. So let's let B1, B2, ... Bn all be disjoint events with positive probabilities, and the sum of all the probabilities is 1. And A is any event with a probability greater than 0. Then the probability of B given A is the probability of A given B times the probability of B over all the probabilities. So the probability of A given B1 times the probability of B1, probability of A given B2 over the probability of B2, and so on and so forth, right? So for this, we definitely need to do an example. So looking only at Gen Xers, Boomers, and the silent generation, silent generation, what's that? The percents for the three groups are 38.6% for Gen Xers, 45% 15.7% for boomers and 15.7% for the silent generation. Okay, so that's the percentage of the population, right? That's going to add up to 100. Also, 91% of Gen Xers use the internet, 85% of boomers use the internet, and 78% of the silent generation use the internet. So I want to figure out what percent of internet users from these three groups are Gen Xers, what percent are boomers, and what percent are the silent generation. So I'm given the probability of being a Gen Xer is 0.386. The probability of being a boomer is 0.457, and the probability of being the silent generation is 0.157. So the probability you use the internet, if A is the probability that you use the internet, then the probability that you use the internet given you're a Gen Xer is 91%. The probability you use the internet given you are a boomer is 85%, and the probability you use the internet given that you're part of the silent generation is 78%. Okay, but I want to find the probability given that you use the internet that you're a Gen Xer, a boomer, or in the silent generation. So, what percent of internet users from these three groups are Gen Xers, what percent are boomers, what percent are in the silent generation is the point. And just so you know, the silent generation was born from 1928 to 1945. Because I had to Google that quick because we needed to know. Okay, so let's use Bayes' rule. So I need the probability of B1 given A. So this is for Gen X. So the probability given that you use the internet, that you are a Gen Xer. So I have to take the probability